Assalamu alaikum. Welcome to the class. This is lecture 3 for the current week, and course code is CS430, and course title is Microprocessor Programming and Interfacing. Before we start today's lecture, we have to discuss previous lectures main points. So in previous lecture we have discussed following pins of microprocessor: 808 and 806. First of all, we discussed clock input of microprocessor. Then in connection of the clock signal, we discussed reset signal and ready signal. And then we discussed taskbar pin, and we learned that taskbar pin logic level will be checked whenever there is a wait instruction in your program. Then we discussed RD bar pin and WR bar pin. RD bar will be enabled whenever microprocessor 808 and 806 will be accessing uh, memory or IO for read operation. And WR bar pin will be activated whenever microprocessor has to perform some write operation to memory or IO. Then there was a signal IO/M bar for 808 microprocessor. In case of 806 microprocessor, M/IO bar signal was discussed. Whenever microprocessor accesses memory, then IO/M bar pin will be having logic 0, and whenever microprocessor 808 is going to access IO, then IO/M bar will be having logic 1. In case of 806, M/IO bar pin will be having logic 1 when memory will be exist, and when microprocessor 806 has to access IO, M/IO bar pin will be having logic 0. Then we discussed that minimum maximum pin will be selecting minimum mode operation or maximum mode operation for microprocessor 808 and 806. If we apply logic 1 at maximum pin, minimum mode operation will be selected, and when minimum maximum pin is having logic 0, then maximum mode operation will be selected. Then we discussed interrupt pins present on the IC package of 808 806 microprocessors. First pin is INTR, interrupt request pin, where IO devices will be placing their interrupts, and response of those interrupt signals will be generated at INTA bar, interrupt acknowledge pin, and that will be a logic 0 pulse. Then we discuss NMI pin of microprocessor, that is another interrupt input pin, and as the name shows that this pin cannot be masked or disabled, while INTR pin may be disabled or enabled by using interrupt flag. Detail of these three pins will be discussed in interrupt chapter. Then we discussed DMA request pin, that is hold pin, and HLDA pin, DMA acknowledge pin. We discussed that IO devices will be placing DMA request at hold pin, and microprocessor will be responding acknowledging the request by placing logic 1 at HLDA pin. Detail will be discussed in DMA chapter. Then we discussed SS not bar pin for 808 microprocessor, that is an status signal, and we discussed a table of IO slash M bar, DT slash R bar, and SS not bar for discussing different bus cycles and states of 808 microprocessor. Then there was a signal BHE bar, bus high enable, for 8086 minimum mode operation. So we discussed that whenever microprocessor 8086 is going to communicate through higher data lines D8 to D15, then BHE will be having 0, and detail will be discussed in memory interface chapter. Then we discuss status signals of 8088 microprocessor S3 to S6, or in case of 8086 status signals are from S3 to S7, and we discuss these signals in detail. So that is the review of previous lecture. Now we are going to start our today's lecture. In previous class we have discussed a table for listing different age-rated microprocessor bus cycles. In that table you are having 6 bus cycles: opcode fetch, memory read, memory write, IO write, and interrupt acknowledge. 5 of these bus cycles are of 4T state, except interrupt acknowledge bus cycle. So in today's lecture we are going to discuss these bus cycles one by one. So first of all we have to discuss opcode fetch and memory read bus cycle. So you may see that there are 4 T state. T1 means a clock pulse, T2 means second clock pulse, T3 means third clock pulse, and T4 means fourth clock pulse. And for these clock pulse will be combining to make a bus timing of a bus cycle. So first signal shown here is address, dedicated address from A8 to A15. Dedicated address will be appearing from the start of T1 and will remain there till the end of T4. Then another bus is shown, address data multiplex bus AD0 to AD7. After that you may see another bus of 4-bit address status multiplex bus A16S3 to A19S6. For both of these signals you may see that during T1 you are having address, and then address ends from both of these buses, and whenever there is address on address data and address status multiplex bus, ALE is at logic 1. So by using this ALE signal you may latch these address lines, address signals at the output of external latch. And we have discussed the demultiplexing of address from data and status in lecture 1 of this week. Now on T1 onward, on address data multiplex bus, data is to be read, and at status signals, address data status multiplex bus, status is to be appear, and that status will be generated by microprocessor. Then during opcode fetch bus cycle, DT slash R bar should be having logic 0, as microprocessor has to read from memory. In case of opcode fetch, some opcode will be coming, or you may say that some decodable data will be coming from memory. In case of memory read, non-decodable data will be received from memory. So DT slash R bar is 0, because microprocessor has to receive some data from memory. DN bar is activated at the mid of T2. It becomes 0 at the mid of T2 and will remain 0 until the end of T4. So data buffers will be enabled for that duration when DN bar is having 0, and data may be read by microprocessor. Read bar is becoming 0 in at the mid of T2 and will remain active till the end of T4. Because microprocessor has to read data, RD bar is activated and will be reading data from the data bus. As we have discussed that during opcode fetch and memory read bus cycle, IO slash memory will be accessed, so IO slash M bar will be having logic 0 for indication that the generated address is for memory device, not for IO device. The only difference between opcode fetch and memory read bus cycle is the SS naught bar signal. You may see that SS naught bar is 0 for opcode fetch bus cycle and memory read SS naught bar will be having logic 1. So that is the only difference in the timing diagram of both of these bus cycles. In this slide we have to discuss the third bus cycle, that is memory write bus cycle, and this bus cycle is of 4 T state: T1, T2, T3, T4. These are the clock pulses on clock input. So first signal shown here is the dedicated address A8 to A15. These lines will be having address at the start of T1 and will remain there until the end of T4. Then second signal shown is a bus of 8-bit address data multiplex bus AD0 to AD7, and third signal shown is address status multiplex bus A16S3 to A19S6. Both of these buses are having address for T1. So for the duration of T1, ALE is activated, and by using the external latches we may store this address for the duration of whole bus cycle from T1 to T4. After T1, address data multiplex bus will be having data that is to be written to memory or IO. In this case, in this bus cycle, memory will be accessed or data will be outputted to memory through these lines. Status will be appearing from T2 to T4 on address status multiplex bus. So as this is memory write bus cycle, so microprocessor is going to transfer data to memory location, memory device. DT slash R bar is having logic 1. DT slash R bar becomes 1 at the start of T1 and will remain 1 until the end of T4. Then for activating data bus buffers, DEN bar is activated at the mid of T2 and will remain 0 till the end of T4. As data is to be written, so write bar will be activated, not read bar. Write bar will become 0 at the mid of T2 and will be deactivated at the mid of T4 to complete the write operation. Then as we are going to access memory, for showing that the generated address is for memory, IO slash m bar will be having 0 and memory will be accessed, not IO. So that is memory write bus cycle timing diagram. As in the table we have discussed earlier that SS naught bar is 0 for memory write bus cycle. To differentiate memory write bus cycle from the halt state. In this slide we are going to discuss the fourth bus cycle, IO read bus cycle. This bus cycle may also be called as input bus cycle, as an input device will be accessed to read data. Duration of this bus cycle is also of 4 T states, T1, T2, T3, T4. These are the clock cycles appearing on clock input of microprocessor. First signal shown here is the same as we have discussed earlier, address dedicated address A8 to A15 that will appear at the start of T1 and will remain there till the end of T4. Then address data multiplex bus is shown 80 to 87. So for T1 there will be address. Same is the case with address status multiplex bus of 4 bit A16S3 to A19S6. This bus is also having address during T1. Both of these address patterns will be stored on external latches by using ALE signal. So at the output of latches, external latches, these address patterns will be available for the duration of whole bus cycle, or you may say that till the end of T4. Now after T1, address data multiplex bus will be used to read data from input device, and at address status multiplex bus address will be appearing. Now dt slash r bar, as we have declared that this bus cycle is for IO read. So read operation is to be performed from input device. Data will be received by microprocessor. dt slash r bar is having logic 0. At the start of T1 it becomes 0 and remains 0 till the end of T4. The next signal shown is DEN bar. DEN bar is becoming 0 at the mid of T2 and remain active till the end of T4 for enabling the external data buffers. As read operation is to be performed, read bar signal is activated at the mid of T2 and remain activated till the mid of T4. So read operation will be completed before disabling the data buffers. Then IO slash m bar is having 1, as we have to read data from IO, not memory. We have discussed earlier memory read bus cycle, in which IO slash m bar was 0 for all the 4 T states of bus cycle. Now we are discussing input bus cycle. For this bus cycle, IO slash m bar is becoming 1 at the start of T1 and it will remain 1 till the end of T4. Now we have to discuss last bus cycle, IO write bus cycle. This bus cycle may also be uh, called as output bus cycle. This bus cycle is also of 40 states, T1, T2, T3, T4. So these are the clock states, clock pulses appearing on clock input of microprocessor. Dedicated address lines are shown here, A8 to A15. Address will be appearing at the start of T1 and will remain there till the end of T4. Then address data multiplex bus is shown, 80 to 87. There is address during T1, and for remaining of the T states you may see data. Then address status multiplex bus is shown, S16 to S3, S16 S3 to A19 S6. These address data multiplex lines are also having address during T1, and for the remaining of T states, status is there. ALE signal is used to latch these addresses on the outputs of external latches. Before disappearing of address from these address data and address status multiplex lines, ALE will become 0. So whatever pattern of address is present at the input will remain there at the output pins of latches till the end of T4. Now after T1, data is to be written to output device. So data will be placed by microprocessor. So you may see that there is no delay between address and data. Just after disappearing of address from address data multiplex bus, data will appear and that will be written to output device. Just same the case is with address data multiplex bus, address status multiplex bus. So address vanishes, status appears. So now we have to discuss dt slash r bar. dt slash r bar is having 1 because microprocessor has to output data to output device. So data will be transferred through data bus buffers. den bar is to enable data buffers. So den bar is activated at the mid of T2 and it will remain active till the end of the bus cycle. Microprocessor has to perform write operation. WR bar is having 0 at the mid of T2 and will remain 0 till the mid of T4. Now we have to discuss IO slash M bar. IO slash M bar is 1 because microprocessor is going to access output device, not memory. So for declaring that the generated address of 20 bit is for output device, not for memory, IO slash M bar will be having logic 1. As you may see that for memory write bus cycle, IO slash M bar was 0 because at that time you have to access memory. But for IO write bus cycle, IO slash M bar is 1 and SS naught bar is 0 for IO write bus cycle. In the previous slides, we have discussed 5 bus cycles: opcode fetch, memory read, memory write, IO read, and IO write. The 6th bus cycle is interrupt acknowledge bus cycle. Interrupt acknowledge bus cycle will be discussed later when we will be discussing interrupt structure of microprocessor 8088 and 8086. Now we have to move on. In this slide, we are going to discuss DMA request and grant pins and logbar pin for maximum mode operation of 8088 and 8086 microprocessors. There are two pins for DMA request and grant, and both of these pins are bidirectional pins: RQ bar slash GT0 bar and RQ bar slash GT1 bar. So IO devices will be placing DMA request by using these request lines, and response will be generated by microprocessor on the same lines. In minimum mode operation, we were having one input for DMA request, hold input, and one output HLDA for DMA acknowledgement. But here we are having two lines, and these lines are bidirectional. Request and grants will be generated on the same lines. Now next pin is log bar. As we have discussed earlier that in maximum mode there will be coprocessors in addition to the 808 806 processors, and during DMA operation IO devices may be accessing memory also. So peripheral devices may also access memory, and coprocessors may also access memory. So it is needed to lock other peripheral devices and coprocessors when accessing memory by using 808 or 806 microprocessor. So if you want to lock other peripheral devices and coprocessors from buses, you have to place lock colon prefix with an instruction. An example is given here that we are having an instruction of move square bracket 250 hex comma ax. The operation of this instruction is ax will be copied at memory address 250 hex within data segment. So microprocessor has to access memory for writing some data. So whenever this instruction is to be executed, coprocessors and peripheral devices should be locked from accessing memory. For that, you may see that there is a prefix with this instruction lock colon. So when this instruction is executed, log bar signal will become 0, and that logic 0 at log bar pin will be stopping coprocessors and peripheral devices from using buses. So that is the purpose of lock signal, to lock other devices than microprocessor to access buses. In the previous lecture, we have discussed a table for IO slash M bar, DT slash R bar, and SS not bar. That table was for minimum mode operation of 8088 8086 microprocessor. In that table, you were having 6 bus cycles and 2 states of microprocessor. In maximum mode, you are having 3 signals, status signals, S0 bar, S1 bar, S2 bar. These 3 signals are for showing which bus cycle is executing, or in which state microprocessor is at the moment. So that is the table. As these are 3 pins, S0 bar, S1 bar, S2 bar. So there are 8 entries in this table, and there are the same bus cycles: interrupt acknowledge bus cycle, IO read bus cycle, IO write bus cycle, opcode fetch bus cycle, memory read bus cycle, memory write bus cycle. We have discussed these bus cycles in detail at the start of this lecture, and we have also discussed these two states, hold state and passive state, when we have discussed minimum mode operation table. So for quick review, opcode fetch bus cycle is to bring decodable data from memory. Memory read bus cycle is for uh, reading data from memory, and that data will be non-decodable data. Then memory write bus cycle is to write some data to some temporary storage device or temporary storage memory. Then interrupt acknowledge bus cycle is to read the interrupt type number assigned to in IO device. IO read bus cycle is to read data present at an input device. IO write bus cycle is to write data to an output device. The detail of interrupt acknowledgement cycle will be coming in interrupt chapter. So what is interrupt type number, that will be discussed later. Now halt state is in which state microprocessor does nothing externally as well as internally. That state is called halt state. And for entering microprocessor into halt state, an instruction is present, HLT. That instruction will uh, bring microprocessor into halt state. For exiting halt state, there are three operations. Either you place an interrupt request at INTR, or you may place DMA request at request grant pins, or you may reset microprocessor by using reset pin. In passive state, microprocessor does its work internally, but on buses there will be no operation. And I have given an example earlier that maybe there is an instruction of shift operation, multiple shift operations, and during that operation microprocessor will not be accessing some data from memory, but microprocessor will be performing shift operation in its ALU. So there is no operation externally, but microprocessor is busy in some operation internally. So that is the passive state. These signals S0 bar, S1 bar and S2 bar is provided to 8288 bus controller for regeneration of the essential signals which are required both in minimum and maximum modes, but in maximum mode those signals are not present on the package of microprocessor 8088, as some of the maximum mode operation signals are has replaced those signals. So next slide is for 8288 bus controller. In this slide we have to briefly discuss 8288 bus controller. IC is shown. IC is of dual inline package, 10 pins per side, total 20 pins, and beside the IC diagram you are having functional diagram of this IC. You may see that S0 bar, S1 bar and S2 bar is provided to this device, and on the right hand you are having some control signals. Memory read control signal is present, MRDC bar, MWTC bar, memory write control signal. Then there is AMWC, advanced memory write control signal. Then there is IORC bar, IO write control signal. Then there is IOWC bar, IO write control signal. Then there is a IOWC bar, that is advanced IO write control signal. INTA bar, interrupt acknowledge signal. Then DT slash R bar, data transmit slash receive signal. Then DEN, data enabling for buffers. ALE, address latch enable. So these signals were present on the package of microprocessor, in minimum mode. But in maximum mode, some of the maximum mode operation signals replace these signals from the package of microprocessor. So by using bus controller, we have regenerated these imported signals to be used in interfacing of memory and I/O. Now we have to discuss instruction queue status signals, QS0 and QS1. These signals are used to show the status of instruction queue. In case of 8088 microprocessor, instruction queue is of 4 bytes, while in case of 8086 microprocessor, instruction queue is of 6 bytes. These queues are used to store instructions fetched from memory. In memory, we store program in the form of machine language, or you may say the hex number. Those numbers are fetched from memory and placed in this queue before execution. You are having a sequence of instructions in memory, and microprocessor fetches first instruction, and microprocessor is executing the first instruction. The subsequent instructions will be moving into instruction queue. When microprocessor finishes executing previous instruction, microprocessor has not to go to memory to pick next instruction, but the next instruction will be picked from instruction queue. So here you are having table of QS0 or QS1 that is showing the status of queue during this operation. So if microprocessor execution unit picks first byte of instruction from queue, status will be 01. At QS1 you will be having 0. At QS0 you will be having 1. And if microprocessor execution unit picks subsequent byte of instruction, then status will be 11 on QS1 QS0. For explaining these two entries of status, you may consider an instruction of 4 byte. So when the first byte of that instruction is picked from queue, status will be 01, and for all the 3 remaining bytes, status of the queue will be 11. Then if you are having an instruction of addition, for example, so when microprocessor will be performing addition, at that time nothing will be taken from queue, so queue will be in idle state, and status will be 00. QS1, QS0 both will be having 00. In the case of transfer of control instructions, program flow changes. So whatever data is present in queue is invalid. Now you have to fetch instructions from the new location. So that's why queue becomes empty and queue is reinitialized from the new location of program. So status for transfer of control instructions will be 10. QS1 will be having 1 and QS0 will be having 0. So these are the maximum mode pins, and now onward we have to discuss internal architecture of microprocessor 8088 and 8086.